The main aim of our design project was to design a system to detect microsleeps, or MSEs. Our project uses a convolutional neural network, an EEG headset, and an electrooculography measurement circuit for this purpose. During an MSE, brainwaves measured by EEG noticeably slow down. Researchers have also found that people tend to move their eyes more slowly in the moments leading up to microsleep. The relevant parts of the brain to measure to detect MSEs are the areas in and around the occipital lobe, located at the back of the head. Therefore, our project emphasizes these areas. Microsleep commonly occurs when people are performing monotonous tasks, such as driving on an empty highway. When an MSE is detected, a simple buzzer mounted on the headset sounds to gently alert the user. When MSEs occur, the individual is usually unaware that they have taken place. For this reason, it is a particularly dangerous phenomenon while driving or operating other heavy machinery. Research shows that people with sleeping disorders or who work irregular shifts are up to 3 times more likely to be in a car accident, and therefore these individuals in particular could highly benefit from our project. With over 1,550 fatalities and 40,000 non-fatal injuries occurring annually in the United States alone as a result of drowsy driving, sleeping while driving is a sizable public health problem. Given that our project could potentially save thousands of lives if widely used, we believe that our project is highly impactful and ethical. We can foresee one way in which our project could be misused, however. Over-reliance on our project in lieu of sensible driving practices like making sure to get adequate rest prior to driving could potentially end up causing more harm than good.
We divided our design team into 3 main groups: the headset team, the software team, and the hardware team. The software team was responsible for creating and training a model that was able to differentiate between a microsleep signal and an awake one. The hardware team was responsible for building a circuit that can amplify and filter the EOG signal and convert it to a digital signal. The headset team was responsible for building a 3D printed headset that is customizable and more comfortable to wear.
So once the raw signal was processed and filtered, we needed a model or an algorithm that could distinguish the microsleep signals from the signals of those that are awake. So in order to do this, we decided to create a convolutional neural network to be able to detect this. Convolutional neural networks are typically used for image classifications, but there are many advantages to it that also make them an ideal use for EEG and EOG signals. Some of these are the first one being that it can work well with noisy data. And this is good because even if the data that is fed into the model has been processed, it's impossible to get rid of all noise. So it's good to be able to work with a model that's robust in noise. The second is the ability to consider spatial structure. So EEG and EOG data are spatial in nature, as in the signals differ from where in the head that you keep these signals. So we need a model that's able to find patterns with keeping the spatial dimensions in mind and can find patterns even with some spatial variation. And the last thing is it has really efficient feature extraction capabilities and can pick up really, really complex patterns, which is needed when working with so much signal data with EEG and EOG signals. So all of these reasons made convolutional neural networks a really good choice. However, in order to create a model, we needed a lot of data. Luckily, we were able to find a source, which we will link and source in our final submission. And this source paper had collected abundant EEG and EOG data for microsleep studies that it's free to use. The data is classified in 4 categories. The first being awake, the second being certainly microsleep, the third being like high likelihood of microsleep, and the last being like an unidentifiable state, which was neither distinguishable of an awake state nor a microsleep state. We used this data to train the model using supervised learning, and this was done in TensorFlow Keras on Python. We tried several different architectures of the model, and ultimately we landed on the following general structure, trying to find a balance between both accuracy and complexity. So the model that we had contained 2 1D convolutional layers following each other, which essentially found patterns in the individual local data and the individual signals. The second thing we had was a pooling layer, which essentially tried to remove some of the spatial variation and the spatial dimensionality in the data. Then we followed this with flattening and dense layers in order to compile the data into a single output. We trained the model and found it to have a 96% accuracy, which is quite high. We then loaded the model into a Raspberry Pi so that it can be used alongside the hardware setup and predict when a signal turns into a microsleep state.
Biological signals are generally quite noisy, so filtering is very important, especially when working with extremely small amplitudes like those found with EOG signals. Generally, the bandwidth of signals relevant to EOG are those from 0.1 Hz to 10 Hz. For the online filtering, we used the first-order low-pass filter with a cutoff frequency of 30 Hz, but found the roll-off wasn't steep enough, so we made it second-order instead. Ensuring 60 Hz in particular was filtered out was important, since the mains run on 60 Hz and therefore induce a lot of noise into everything. For the offline filtering, we simply applied another low-pass filter at 20 Hz and a high-pass filter at 0.1 Hz. We had to use an online low-pass filter to prevent aliasing. The Arduino ADC samples at 10 kHz, and we need around 20 Hz of bandwidth to be on the safe side. Our Nyquist frequency was 3.33 kHz, so our cutoff frequency had to be less than this, hence our low-pass filter.
User signals usually have an amplitude of a few tens of microvolts. Due to this, we needed to carefully select an amplifier that meets all the requirements for EOC application. First requirement is a high input impedance. Since the voltage drop across the electrodes can cause the EOC signal to distort, we need to have a very high input impedance of around 10 megaohms so that the current drawn by the amplifier is minimized. Second requirement is a low capacitive input impedance. EOC signals usually have a frequency of a few hertz. The capacitance can act as a low-pass filter and filter out the high-frequency component of the EOC signal. To prevent these effects, we needed an amplifier with a capacitive impedance of lower than 1 nanofarad. Additionally, we need a high common mode rejection ratio. EOC signals are especially susceptible to noise since the amplitude is very small. Therefore, we must have a very high common mode rejection ratio of around 100 decibels to keep the signal clean. Finally, we need to have a high gain since the EOC signal is of the order of microvolts. We need to have a gain of 10,000 to achieve this gain. We use two stages of amplifiers. We set the gain of 200 for the first stage and a gain of 50 for the second stage, for a total gain of 10,000. We selected AD8237 instrumentation amplifier as it has the input impedance of 100 megaohms and 5 picofarads, common mode rejection ratio of 114 decibels, and a maximum gain of 1,000.
To improve on the BCI headset, we created our own more versatile design. As you can see on my head right now, we have stretchy tops so that we can tighten all the top nodes at the same time, as well as a tightening mechanism for the headband area. It allows for very flexible movement of the nodes, although it stays tight once you have it tight. It is not a one-size-fits-all like the BCI headset. It is instead adaptable and versatile for each user's head to improve on the accuracy of the readings. As you can see here, we have just generic readings from all of the nodes around my head. We have 8 as the BCI board allows for that maximum number.
Some significant price points in our project included amplifiers, like the AD8237, LM358, and the INA118. EOG signals are susceptible to noise, and we needed to choose amplifiers with special features, such as high gain, high CMRR, and low noise. These amplifiers are usually more expensive than normal general-use amplifiers. Another thing that might contribute to a higher price point is electrodes. Silver or gold-plated electrodes are more ideal for EOG and EEG application because of their low impedance characteristics. These electrodes usually cost around $100. To keep our product affordable, we cut down the cost by 3D printing the headset. This way, we can produce a custom-made headset at a lower price.
One of the biggest challenges we faced while working on our project was the strict deadline we were working under. So in only 2 months, we had to come up with an idea, research, prototype, and then test our design as well. Although we were working under such a strict time constraint, we were still able to come up with an impressive final design. This is because we were able to collaborate effectively and always keep our mind on our final goal. In terms of hardware, we had minor challenges with working with surface mount components, amplifying such low voltages, and reducing noise as well. In terms of software, we had some challenges with finding the best architecture for our model, and then after that, balancing the trade-off between how complex the model was and how accurate. One way we could improve our design is by making it more seamless and comfortable. Our current way of collecting data involves the driver wearing a headset on their head, which entails electrodes poking into their scalp. This inevitably is uncomfortable and can be painful, and also more importantly is not feasible for a driver to wear regularly. Another way we could use to innovate or improve upon this is to figure out a way to read data using glasses that the user can somehow wear. This would instantly make our design more seamless and comfortable.